Welcome to you all to this MOOCs online video course Theory of Yarn Structure. In the last two classes, we started discussion on generalized theory of tensile behavior of yarns. We pointed out a few problems related to Gegoff's theory, and there were certain guesses for the solution of Gegoff's theory. One of the guesses was related to fiber orientation. As we know, Gegoff's theory did not consider about fiber orientation. So, it might be possible that if fiber orientation is incorporated and Gegoff's theory is modified, probably there will be a better correlation between experimental results and theoretical findings. So, with that view we started discussion on fiber orientation. In fiber orientation, we discussed what is fiber orientation, what is the intuitive concept behind fiber orientation. Then we talked about planar orientation of fibers in fibrous material in general. There we discussed about two concepts, one is isotropic fiber orientation and the other is anisotropic fiber orientation. And then we continued our discussion and talked about the orientation distribution of non-oriented angles. So, we will start from there. So, often we work with cross sections of fibrous material for microscopic analysis and for other purposes. So, in while studying fiber orientation with the section, then we talked about two dimensional orientation of fibers in a section or planar orientation of fibers in a section. Now, so what we do when we try to measure fiber orientation in yarn, for example, then we put the yarn in some paraffin wax, we harden it for 1 day keeping in the refrigerator, then we take out and we use microtome and we obtain a slice or the cross section of the yarn. Then we try to analyze the fiber orientation using some microscopic arrangement. So, in such cases we often encountered with a image of this kind. So, what we see here? We see here is a fibrous prism. So, this fibrous prism has a volume A multiplied by B multiplied by C. So, the volume of the prism is ABC. In this prism we see one sectional plane. The sectional plane, let us use red color for this sectional plane. We name this sectional plane as sigma, right. Now, there are many numerous fibers or fiber segments present in this sectional plane, in this fibrous prism. Now, when we use this sectional plane, say let us now consider about one fiber segment. So, there are many fiber segments. For example, this is one fiber segment, its name is 1. Also there are many fiber segments, number 2, number 3 and so on. Now, let us think about number 1 fiber segment. It has two ends, one is the lower end A, another is the upper end B. The lower end A is lying on the sectional plane sigma, right, and this fiber segment is having an inclination theta from the normal to the sectional plane. So, theta is here non oriented angle, it can lie from 0 to pi by 2, right. Now, there is another sectional plane which is then named as sigma prime. So, let us use blue color to denote that sectional plane. The position of this sectional plane is determined by the upper end of the fiber segment 1. What is the upper end of this fiber segment 1? That is point B. So, the point B is touching the sectional plane named as sigma prime. What is the distance between these two ends? The distance between these two ends A and B is h, right. So, there are numerous fiber segments which will be intersected by these two sectional planes. However, there could be also many fiber segments which will not at all be intersected by these two sectional planes. For example, fiber segment number 2, fiber segment number 3, they are not intersected by these two sectional planes. However, they are present in the fibrous prism. Now, we assume that fiber segments having inclination theta, obviously theta is a random variable. So, different fiber segments will have different values of theta, but those fiber segments are uniformly distributed in this prism. Then the volume portion of the intersected fiber segments inclined at an angle theta in the prism is. So, the question is now, what is the ratio of volumes of the intersected fiber segments inclined at an angle theta? Now, if a fiber segment is intersected by these two planes, then must be its upper end should lie in between these two planes sigma and sigma prime. So, the volume occupied by the intersected fiber segments will be the ratio of the volume of these two, the volume of this space in between these two sectional planes, that is length into breadth into height, divided by the volume of the entire fibrous prism, that is A multiplied by B multiplied by C. Right. So, this A and B are cancelling out, we are left with H by C. What is H here? H is equal to delta L cos theta. What is H? H is the distance between two ends A and B. What is delta L? Delta L is the infinitesimally small length of fiber segment AB, and theta is the angle of inclination of the fiber segment from the normal y axis to the sectional plane sigma. So, we see that H is equal to delta L cos theta. So, we obtain this volume portion is equal to delta L cos theta divided by C, right. So, this is the expression for volume portion of intersected fiber segments which are inclined at an angle theta in the fibrous prism. So, the fiber segments are intersected by these two sectional planes sigma and sigma prime. Now, let us use the meaning of some symbols. Capital N. Capital N is the total number of fiber segments in the prism. As I said you earlier, there are numerous fiber segments present in the prism, the entire prism whose volume is A into B into C. So, obviously, this number n is very high. What is u theta? U theta we learned in the last class. This is the probability density function of non-oriented angle theta. Probability density function of non-oriented angle theta. What is non-oriented angle? That we have discussed in the last class. Theta is lying from 0 to pi by 2. This we have extensively discussed in the last class. So, what is u theta d theta? If u theta is the probability density function, then u theta d theta is the relative frequency. Relative frequency of fiber segments in an elementary class which is ranging from theta to theta plus d theta, right. So, then what is the meaning of n multiplied by u theta d theta? N multiplied by u theta d theta is number of all fiber segments which are falling in this elementary class. clear. Then what is the number of intersected segments which are falling in this elementary class? So, there were numerous fiber segments. So, this is the number n u theta d theta, but among these fiber segments there will be a few or some fiber segments which will be intersected by those two sectional planes. What is that number? So, let us go to the next page. Number of intersected fiber segments falling in the elementary class starting from theta and ending at theta plus d theta. Is dn, which will be equal to, what is the total number of all fiber segments in the prism? N u theta d theta, and what is the probability? Probability is p theta. We have earlier found out this probability. So, this is the volume portion, right. So, this is the number of all fiber segment present in the prism, and this is the volume portion occupied by the intersected fiber segments. So, this is the number of fiber segments falling in the elementary class. Now, so this is the number of fiber segments falling in the elementary class. Now, what is the total number of all intersected fiber segments? If we integrate it from theta is equal to 0 to theta is equal to pi by 2, we will find out the total number of intersected fiber segments in the assembly. N, which is basically the integration of dn when theta is equal to 0 to theta is equal to pi by 2. Why the lower limit is 0? Because theta is a non oriented angle. N u theta d theta into p theta. What was p theta? P theta was equal to del L by C. So, if we substitute, this p theta is equal to del L by C, then we obtained n is equal to integration 0 to pi by 2 n into del L by C u theta d theta. So, into cos theta. So, let us write it once again in a more correct form, 0 to pi by 2 n del L by C u theta cos theta d theta. So, this is the number of intersected fiber segments, total number of intersected fiber segments. Here n delta L by C is a constant, so it can come out of the integration. N delta L by C is a constant, so 0 to pi by 2 u theta cos theta d theta. So, if you solve this integral, then you will be able to know the total number of fiber segments, intersected fiber segments present in the prism, right. Now, u theta was the PDF of non-oriented angle theta, but this non-oriented angle theta was related to the fiber segments. What is about the intersected fiber segment? So, definitely they will have another PDF. So, let us consider that PDF as u star theta. So, we mean u star theta PDF of orientation of intersected fiber segments. Try to understand the difference between these two terms, u theta and u star theta. U theta, as we explained earlier, was the PDF of fiber segment, which will have angle ranging from 0 to pi by 2, non-oriented angle. But u star theta is the PDF of orientation of intersected fiber segment, because all fibers will not be intersected by the sectional planes. There will be only few fibers will be intersected by the sectional planes, and obviously u theta and u star theta will be different. They are different PDFs. So, how to find out this PDF u star theta, or we can frame this question in a different manner. What is the relation between u theta and u star theta? So, let us derive that. What is the meaning of u star theta d theta? This is definitely relative frequency, but relative frequency of what? Relative frequency of intersected fiber segments falling in the elementary class starting from theta to theta plus d theta, intersected. This is what makes the entire things different, right. Then what is the meaning of u star theta d theta? This is the relative frequency. Relative frequency is defined by frequency divided by total frequency. So, what is the frequency? Frequency is dn. What is the total frequency? Total frequency is is small n. So, u star theta d theta is equal to frequency divided by total frequency, right. What is dn? dn we have derived earlier, that is your n del L by C cos theta u theta d theta. This we have derived today, n del L cos theta u theta d theta, and what is small n? That also we have derived today. Small n is integration n dl n del L by C integration 0 to pi by 2 cos theta u theta d theta. So, these two we have defined derived today. So, what it becomes is u theta cos theta d theta divided by 0 to pi by 2 u theta cos theta d theta. Now, this d theta and this d theta are cancelling out. So, we are left with u star theta is equal to u theta cos theta by integration 0 to pi by 2 u theta cos theta d theta. Let us assume this denominator is equal to coefficient k n. So, this integration 0 to pi by 2 u theta cos theta d theta is equal to coefficient k n. This coefficient k n we have discussed in module 2. So, we obtain u star theta is equal to u theta cos theta by k n. This is an important relation. That means, what is the PDF of intersected fiber segments in a prism? This is the expression of that PDF. So, this expression is very important. So, if you see, we have discussed many forms of probability density function. We started with f naught psi naught PDF of isotropic orientation in plane. Then we talked about PDF of anisotropic orientation in plane. Then we talked about generalized PDF when the preferential direction is not y axis, but preferential direction is situated at an angle beta from y axis. Then we talked about PDF of fiber orientation in a section. Today we have talked about PDF of intersected fiber segments in a sectional plane. So, this all we have discussed. So many PDFs we have discussed so far, they are all different. Now, we are left with a small part of fiber orientation, that is how to find out number of fibers in a section, that we would like to study now. Number of fibers in a section, that we would like to study now. So, again we are discussing about planar orientation, that is two dimensional orientation. 2 dimensional what you see is an image. Now, let me explain you this image. You see a lot of fibers or fiber segments are present in here, and so you are seeing that this is an x axis and this is y axis, and preferential direction is not y axis, but it is some angle. Here it is alpha, in the last class we considered it as beta. So, let us consider it as beta, right. Then we additionally we see that there is a very thin, very slim slot which is perpendicular to y axis. So, this is the slot, very thin, which is perpendicular to y axis. In this slot there are very small fiber segments are intersected. Let us use some green color for those, say this. So, there is a long fiber, but this slot intersects a small segment. This is one, this is another, this is another, this is another, this is another. These all small fiber segments are intersected by this slot. We use green color for them, right. Then also what we see is that this slot has a length c and thickness delta h. Thickness is very small, but the length is very large. So, length is c and thickness is delta h. So, this is all about this image. Now, let us define some variables here. C, what is c? C is the length of the slot. Delta h is the thickness of the slot. Capital N is the number of all intersected fiber segment. Green color we have used for them. Right. And these intersected fiber segments, let us use some subscript, say I, for to use them. 1, 2, likewise n is the sequence of intersected fiber segments. Right. Now, this fibrous assembly is having a mass, weight. Let us consider this G, capital G is the mass per unit area of the fibrous material. Also, we discussed rho, fiber density, module 1. And also we use this relation S star by S cos theta. What is S star? S star is the sectional area of a fiber segment and capital S is the cross sectional area of a fiber segment, theta is the angle of inclination. Now, obviously there will be many sequence, so we can use a subscript here like this. We assume all fibers have same cross sectional area, so we do not put any subscript here, right. So, theta I is the angle of inclination of the fiber segment. All right. Now, we proceed to find out number of fibers in a section. What is the mass of ith fiber segment? Can you tell us what is the mass of ith fiber segment? Suppose this is the first fiber segment, what is the mass of this segment? This is the second fiber segment, what is the mass of this fiber segment? Likewise, there are many fiber segments which are colored by green. So, what is the mass of these green colored fiber segments? How to find out that theoretically? Mass is equal to volume into density. What is density? Rho. And what is the volume occupied by this fiber segment? Sectional area Si star into delta H. So, that is the volume occupied by this fiber segment. So, the mass of the ith fiber segment is Si star into delta H, that is the volume into density, then it gives the mass. So, let us now write down this mass of ith fiber segment intersected, very important word. Let us use is S I star delta H, this gives you the volume into density gives you the mass. So, this is ith fiber segment, there are capital N number of fiber segments. So, what is the total mass of all fiber segments intersected? This is this is equal to summation of Si star delta H into rho, I is equal to 1 to I is equal to n, right. Here in this summation expression, delta H is a constant, thickness of the slot, rho is also constant, density of fiber. So, these two constants can out of the summation. So, we obtained this expression. Okay. So, now this is the mass of the total mass of the all intersected fiber segments. So, mass per unit area capital G is equal to this mass divided by area. What is area? Area is length of this slot was C and thickness of the slot was delta H. So, area is C into delta H. So, mass per unit area G is equal to delta M mass by C into delta H, right. So, we write delta M is delta H into rho into Si star I is equal to 1 to n C into delta H. So, this delta H are cancelling out, what we are left with rho C Si star summation. Now, in order to make this expression more meaningful, we rearrange this expression in a special form. What is that form? Let us multiply and divide this expression by capital N. What is capital N? Capital N is the total number of fiber segments. So, what we obtain is N by C into rho Si star by capital N. Right. Now, you look at this expression very carefully. What is your capital N by C? Total number of sectioned fiber segments. C is the length of the slot. So, this indicates number of intersected fiber segments per unit length. So, N by C, this expression indicates number of intersected fiber segments per unit length of the slot. Let us give a new symbol for that new, and rho is fiber density. And what is this one? Summation of all sectional areas divided by total number of fiber segments. This is the mean sectional area. So, our earlier expression we write it as nu rho star, right. So, mass per unit area capital G is equal to number of intersected fiber segments per unit length into density of fiber into mean sectional area. So, if we rearrange this expression by rho into a star, right. Let us further work on this expression in order to get some interesting information about this. So, nu is equal to G by rho into 1 by star bar. What we do? We use the density of the material, we multiply and divide. So, we write this is the density of the material rho star and density of fiber is rho star by rho into 1 by, right. Now, look at this term. What is this term? Density of the material divided by density of fiber. This is one of the interpretations of packing density, interpretation of packing density. So, this is basically is equal to mu packing density. So, what we see is that this by this into packing density into 1 by a star bar, right. All right. Now, we can further work on this expression. How we can work on this expression? We can also substitute here this Kn then we can also rearrange this expression. Now, further we can write this expression. Look at this term. What is this term is talking about? Mass per unit area of the material divided by density of the material. So, this ratio is the inverse of thickness. What was the thickness of the slot? Del H. So, this is actually your del H. So, delta H into mu into 1 by a star, right. So, this we can further write as delta H into mu into Kn by S. So, nu becomes delta H mu Kn by S. So, you get a meaningful expression how you can find out experimentally this value. Right. So, it is now possible to find out experimentally what is the number of fiber segments per unit length. Delta H, you will cut the section. So, you know what is the thickness of the section. You can use a vernier calipers to measure the thickness of the section. So, this will be known to you. Packing density is also possible to evaluate experimentally by using cross sectional analysis with the help of microtome and image processing technique. Coefficient Kn is also possible to evaluate experimentally. You can find out the cross sectional area of the fiber, you can find out the mean sectional area of the fiber. So, you can also find out Kn and also you can measure the cross sectional area of the fiber S. So, what we can see is that in principle this value can be obtained experimentally using this expression. This is a very useful expression often used for practical measurement. Right. Now, this ends the theoretical discussion on fiber orientation. If you recapitulate what we discussed in the last 3 hours approximately on fiber orientation, we started with the intuitive concept of fiber orientation. Fiber orientation refers to the angular disposition of very infinitesimally small fiber segments, unitary vector. Then we talked about planar fiber orientation or two dimensional fiber orientation, concept of isotropic fiber orientation, concept of anisotropic fiber orientation. We used a model based on the idea of flexible belt with perpendicular spikes, how fiber orientation is changing from isotropic to anisotropic one. As a result, we derived an expression for PDF of anisotropic fiber orientation. We came to know measure of anisotropy parameter C. Higher is the value of C, higher is the anisotropy of orientation. Then we generalize this orientation distribution function, probability density function of fiber orientation, by considering a preferential direction which may not be same as y axis. In that case, what is the PDF that we have derived? Then we started with the section orientation, planar fiber orientation in a section, the concept of but before that we discussed about the non oriented angle. When earlier the angle was ranging from minus pi by 2 to pi by 2, often we need to work with positive angles 0 to pi by 2. In that case, how we obtain the probability density function, that we have discussed, angle comes theta there. Then we discussed about the probability density function in a sectional plane, the concept of u theta, PDF of theta we derived. Then intersected fiber segments, what is the orientation of intersected fiber segments, u star theta, that we have discussed today. Finally, we obtained an expression for number of section fibers per unit length of a material. This function we often use experimentally. Now, why we do all these things for fiber orientation? The reason I stated you earlier, there were certain problems in Gegoff's theory that we have addressed. Why those problems were occurring, that we do not know yet. We thought it was a guess from us that maybe fiber orientation was not included in Gegoff's theory, that brought the problem of mismatch between theoretical and experimental results. So, we will incorporate the effect of fiber orientation in tensile behavior of staple fiber yarn, and we will then cross check, compare between Gegoff's theory and the modifier theory. So, that is why it was necessary for us to know about fiber orientation, and that was the reason we learn about fiber orientation in this module. Now, with this knowledge of fiber orientation, we will be now going for deriving a generalized tensile mechanics of staple fiber yarn. But before that, whatever we have learned so far on fiber orientation, we would like to solve certain numerical problems, so that we will be able to correlate with this theoretical understanding with the practical examples, and our aim is to learn better about fiber orientation. So, we will start a few numerical problems on fiber orientation before we go for deriving a generalized mechanics of tensile behavior of staple fiber yarn. So, these numerical problems on fiber orientation we will discuss in the next class. Thank you for your attention.